In this video, we'll talk about some practice problems related to the key variables for studying an object's motion. And so we remember there are position vectors, velocity vectors, and also the acceleration vectors discussed in the key variables section. So now let's look at some example problem about that. Question 1. An object's position is described by the following vector, and where all quantities are in SI units. What are the instantaneous velocity and acceleration of the object at t equals 3 seconds and 4 seconds? What are the average velocity and acceleration between t equals 3 and 4 seconds? We're going to solve this problem with exactly the definition of these two quantities, velocity and acceleration. The instantaneous velocity is given by the time derivative of the position vector, and when you take a derivative of a vector quantity, you will take the derivative of each component independently. In our examples here, we have 3t squared for the x component. So the derivative of that gives us 6t, because we bring down a factor 2 to multiply with 3. It's I hat. And then second terms here for the y direction, we get 4 j hat. Last term, we bring down a factor 3, and that gives us negative 6t squared times k hat. Now all quantities are in SI units, meaning when we get this result here, the unit should be in meters per second. That's the SI unit for velocity. And acceleration is the second derivative of this. So, and second derivative of r, and then first derivative of v. So let's continue with this derivative with respect to time for the v. And so I start from here, and then the first term here will be 6 I hat. Second term is a constant, so it disappears after the derivative. The third term, negative 12 times t k hat. The unit here should be in meters per square seconds. Okay, so that's the v and a, and those are instantaneous velocity and acceleration. Now, remaining thing here is to plug in the values 3 seconds and 4 seconds. So let's write this down. So v at 3 seconds equals, when I plug in 3 here, I get 18 I hat. 4 j hat. When I plug in 3 here, I get 54 k hat. Okay, and then the unit again, see, meters per second. Now the velocity at 4 seconds, we can do that calculation similarly, and then the first term will be 24 I hat 4 j hat minus 96 k hat meters per second. Now let's do the acceleration A. So acceleration A at 3 seconds equals 6 I hat minus 36 k hat meters per square second. The acceleration at 4 seconds equals also 6 I hat minus 48 k hat meters per square second. Okay, so those are instantaneous quantities. So let's look at the average velocity and acceleration between 3 seconds and 4 seconds. Okay, let's recall the definition for average velocity. It's given by delta r over delta t, and delta r refers to r at 4 seconds subtract r at 3 seconds and then divided by the time difference, which will be 4 seconds minus 3 seconds. Okay, let's see. Now, in order to plug in numbers here, I actually need to calculate r at 4 seconds and 3 seconds. So let me start a new calculation here. So r at 3 seconds equals, when I plug in 3 here, I get 27 I hat. Now the second term will be 12 j hat. The third term is 54 k hat. The unit here is in meters. Now r at 4 seconds equals 48 I hat plus 16 j hat minus 128 k hat in meters. Okay, so I can do the subtraction here. So delta r is this subtract that, so we get 21 I hat plus 4 j hat minus 74 k hat. Okay, so let's copy this here. Divided by 1 second, and that's in meters. So we get, in the end, 21 I hat plus 4 j hat minus 74 k hat meters per second as the average velocity. Now, average acceleration will be easier now because I need to do delta v delta t, and that's v at 4 seconds minus v at 3 seconds, and then divided by 1 second. And we actually already have the two v's here, right? These two. Let's figure out what's delta v. So the first term, 24 minus 18, is 6 I hat. Second term disappear, they cancel. The third term is negative 42 k hat, and that's in meters per second, and the denominator is in 1 second. So it gives us 6 I hat minus 42 k hat meters per square second. Okay, so these two quantities are the average velocities and accelerations between this time interval. So now we can see that compare with the velocity, for example, at 3 seconds and 4 seconds, the average velocity is in between these two values, right? So you can see the first term, 18 and 24, 21 is in between, right? And 4 and 4 here, because it's a constant, so we also have a constant here for the average velocity. Now 54 and 96, I have 74 here. That's in between these two values. And similarly, you can check that for the acceleration, average acceleration. Okay, so that's question 1. Now here's question 2. A particle's velocity is given by Vx equals bt squared, where b is a constant and t is in seconds. At t naught equals 0 second and x naught equals negative 10 meters per 10 meters. At t1, we know the time instant 3 seconds, and then we know x1 is 15 meters. What is the value of b? Now for this problem, we need to do integrals, and then let's say, and then we can use the these two conditions, initial and instant one information to solve for B. So let's recall the velocity is dx dt. Okay, so now if I move dt to the left side, I get vx dt equals dx. Okay, and then let's do the integral on the two sides, and then we start with, let's say, x naught here to x1, and then the time integral goes from t naught to t1. Okay, and then after I do the integral and then substitute in the values, I should be able to calculate the constant b. Okay, so let's do that. Now I need to plug in the expression for Vx, which is bt squared dt, and then the lower bound t naught, upper bound is t1. The right side is easier because we integrate over 1, and then the result here is simply just x1 minus x naught. Now let's see the left side. The left side b is constant, so it doesn't affect the integral. So we have 1/3 b t cubed, and then t goes from t naught to t1. Okay, and then we can plug in the upper bound t1 cubed minus t naught cubed equals x1 minus x naught. Therefore, the value b is given by 3 times x difference divided by t difference, t cubed difference. Now we can plug in all the numbers. So we have x1 equals 15 minus negative 10. Okay, so be careful that you need to keep the negative sign for this value of x naught, and then 3 seconds cube minus 0 cube. Okay, and then the final value is 25 over 9. Okay, so that's the constant b, and b should also have a unit, right? Because we need to satisfy the left side here is meters per second, and the unit should be consistent left and right side. Now we have square here for the time, second squared, right? So we need to have meters per second cube, per second cube as the unit for this quantity b. Okay, so that's the second example. Now, third question. An object's position as a function of time is shown below. What are the instantaneous and average velocities between A, 0 second to 1 second, B, 1 second to 3 seconds, and then C, 3 seconds to 5 seconds? And then further, we need to calculate question D, what are the total distance and displacement of the objects between 0 second and 5 seconds? So we're looking at the whole range of these objects' motion, and then that's the difference between conceptual difference between distance and displacement. We need to calculate that difference. Now, question E, what are the average speed and velocity? So again, that's the difference between speed and velocity. Speed is the scalar, and then velocity is a vector. We need to take that into account during the calculation. Okay, so the for question A, instantaneous and average velocities between 0 and 1 second, they're actually the same, because we know the velocity, to be exact, instantaneous velocity is the instantaneous slope. Okay, and then the average velocity is the average slope. Okay, so now if I draw that for, let's say, instantaneous velocity at one instant, it will coincide with the average slope. Okay, so they're actually the same. So that's why there's no difference in this case here. So let me write this down. So the average velocity equals instantaneous velocity, right? And then when we calculate average velocity, we do delta x over delta t to calculate the slope. Delta x refers to 8 meters minus 0 meters. And then the delta t here refers to 1 minus 0. So we get 8 meters per second as both the average velocity and instantaneous velocity throughout this time interval. The let's see, the second question B is between so here is between 0 second to 1 second. Now it's 1 second to 3 seconds. So between this, the slope here is flat, so it should be 0. Okay, you can also see that in the numerical calculation. So we have delta x over delta t, where we have 8 minus 8 and 1 minus 0. Okay, so we get 0 here. C, between 3 seconds and 5 seconds. Again, they are equal, and then delta x is given by 0. The final point is 0 x, and then 8 meters for x at the beginning. So it's 0 minus 8 divided by 5 minus 3. So we get negative 4 meters per second. Now question D, what are the total distance? So I'm going to use the symbol S to represent distance. So total distance should be the summation of all the distance in each section, right? So between 0 and 1, the distance is 8 meters, and then between 1 and 3, so that would be 0, right? So the object is not moving, so it would be 0. And then lastly, again, we go from 8 meter to 0 meter. Distance traveled is 8 meters again. So that's why we have total distance equals 8 meters. That's the first section, plus 0 meters, and then plus again 8 meters. So we get 16 meters. Now the total displacement, that will be, let me call it delta x. The symbol is delta x, and then we should look at the final position at 5 seconds, subtract the initial position at 0 seconds, and we see that both are 0 here. So that's why we get 0 minus 0, you get 0 meters as the displacement, total displacement. Now question E, the average speed and average velocity between 0 and 5 seconds. So average speed, let me call it Vs. S corresponds to the S symbol here for the distance. So Vs is given by S over delta t. S is 16 meters. Delta t is 5 seconds. So we get 3.2 meters per second as the average speed. And the average velocity, let me call it Vx equals delta x over delta t, and then we get 0 here, 5 seconds, so equals 0 meters per second. Okay, so we can see that the average velocity is actually 0 throughout this process. Okay, so I hope that these practice problems clarify some conceptual understanding of the key quantities in kinematics. Okay, and if you have any questions, leave me the comments. Okay, thank you for watching.